Hello everybody, my name is Mateus. I am a PhD student from the Faculty of Human Kinetics, and I'm going to present you my work entitled Individual Muscle Contributions to Knee Bone-on-Bone Forces occurring during a maximal forward braking and backward acceleration in elite athletes. Bear in mind that this work is a collaboration between the Interdisciplinary Center for the Study of Human Performance from the Faculty of Human Kinetics and the High Performance Center from Catalonia. So, in professional sports, sudden changes of direction are needed to perform at the highest level. However, when inappropriately performed, one can impose mechanical loads at a joint that are higher than it can bear. So, the athlete is at a higher risk of joint injury. So, that's what we want to prevent. Recent studies show that deceleration-based tasks are more frequent in elite sports than acceleration-based tasks, as you can see from the study on your left. This is a literature review and a meta-analysis that show that how they favor the deceleration along the sport. And they can also impose higher mechanical loadings on the joint, as you can see from the study on your right. Which is a review of elite sports and soccer. And they show that the deceleration-based tasks are mechanically more imposing on the joints than acceleration-based tasks, and others around 70% larger. So, as you can see, a greater insight on how the joint is loaded during these tasks is very important for us to understand how to prevent the injuries and how to enhance their performance. So the main goal of this work stands in the identification of the main muscle contributors to the knee bone-on-bone forces, whilst performing maximal forward braking and backward acceleration task in elite athletes. So for the study, 14 elite male athletes were participated in the study. They were injury-free, and the data acquisition occurred at the High Performance Center of Catalonia. Kinematic and kinetic variables were attained using 8 infrared cameras synchronized in time and space with 2 force plates. For the kinematic data, it was also used 28 passive reflective markers. For the task in itself, the participants were required to sprint at their maximum speed up to the force plate, brake with their dominant lower limb, and then run backwards. As you can also see, this task can be divided into 2 distinct phases. Firstly, a deceleration phase where the athlete has to dissipate energy, thus braking, and then the backward acceleration phase where the athlete is required to perform a speed change in order to run backwards. For the results, we are going to show you the results in terms of these distinct phases. So for the data processing, the biomechanical variables were processed using the Qualisys Track Manager software, and the inverse kinematics problem was performed using a global optimization step or approach using the Visual 3D software from the company C-Motion. From this analysis, we obtained the joint angles, the scale factors which will then be used for the scaling process of the musculoskeletal pipeline, and also the ground reaction force data. From then on, we go to the main workflow of this project, which is the musculoskeletal simulation part. For this part, we start with a generic model, and the model is a 12 rigid body, 29 degrees of freedom model, and we use the software OpenSim and its MATLAB API. So since we start with a generic model, we have to scale it to match each subject's anthropometric measures. So that's why we perform this scaling step, and we use the scale factors obtained from Visual 3D before. From then on, we performed the residual reduction algorithm step, and this step was inserted in the pipeline in order to minimize dynamic inconsistencies due to errors during the data acquisition or even modeling assumptions. After this, we performed the main part of this work, which is the muscle force estimation. And the estimated muscle forces were the protagonists for this workflow, so that we could estimate the individual muscle contributions to knee bone-on-bone forces. And this method we based on the work of Sasaki, which is an author that presented the paper in 2010. For the results, we can see that anteriorly directed, compressive, and medially directed knee bone-on-bone forces occur during this task, and which was natural from the nature of the movement. The larger forces occur along the anterior-posterior direction. So going one by one, let's start with the anterior-posterior direction. We can see that the main contributors to the knee forces along this direction are the vasti, followed by the hamstrings, so the main muscle spanning the knee joint, followed by the rectus femoris. A noteworthy contribution along this direction are the soleus, which does not span the knee muscle. However, they contribute during the deceleration phase along this direction. Going to the vertical components of the knee bone-on-bone forces. Once again, the vasti are the main contributors, followed by the hamstrings. However, looking at the soleus contributions, we can see that it is constant throughout both phases, which does not occur during the anterior-posterior direction. Along the mediolateral direction, there is not much to say, since the vasti are the protagonists and they perform most of the contributions to the knee loading along this direction. Comparing our results to the literature, we can compare it to a previous study from our research group, dated back from 2020. Which estimated the individual muscle contributions to ground reaction forces during this task using a musculoskeletal simulation approach. However, they noted in that work that the hamstrings counteracted the effect of the vasti, since the vasti were the main contributors to the ground reaction force along the horizontal direction. So they contributed the most to the breaking of the center of mass, which we can see also from the results of our work. However, we see that the hamstrings tend to load also the knee and not unload, which would be expected if we only looked at the results from the article that I present to you. However, if we compare to another study which estimated individual muscle contributions to ACL loading during a stop jump task, which dates from this year, although it is a different task, we can reach the same conclusions, which are that not only the main knee extensor muscles act to load the ACL, or in our case the knee joint, but also the hamstrings, which would naturally unload from what we previously know the ACL. They tend to load as well the ACL during this task. So it gives us confidence that our results may be correct and may provide a better understanding of this task. So in a note of conclusion, we can see that the vasti are the main contributors to these forces along all three directions. We can also see muscle contributions from muscles that do not span the knee joint, for example, the soleus. And with this pipeline, we believe that we can gain a better understanding of the necessary mechanisms to perform this task, and also a possible approach to study knee injury mechanisms and evaluate these task injury risks during injury prevention protocols. Here I can show you the references that have been presented throughout the presentation. And with this, I end this presentation. So thank you for having me.